Welcome. In this video, we're going to go over problems 5 and 6 from the stoichiometry AP release here. And this first one's a gravimetric analysis one with a percent by mass, which is a really good problem to review. This is a really good one. And if you think about what's happening here, we've got a copper silver alloy. Okay, and that just means a mixture. It contains copper and it has silver. We don't know what else. We don't know what ratio they're in. There is no such thing as a molar mass of this alloy. Okay, we don't know. What we do know is if we take this alloy, it has copper and silver in it, and we know that it weighs 0.6489 grams. And if we take this thing and we dissolve it in some nitric acid, which we did this in a lab back in probably September. Remember, we did the reaction where it turned blue and it released this brown gas. It was a cool reaction. What that reaction does is it basically dissolves your metals and turns them into ions. So when you add nitric acid, it dissolves, and that means you end up with copper ions and silver ions. There's other stuff in the solution too, but they're spectators. We don't really care about them right now. And so after it completely reacts, we've got these ions, and we're going to add a bunch of sodium chloride. So we're going to add excess sodium chloride. We're going to keep adding it until no more precipitates formed. So we don't have excess sodium chloride. So we're adding some sodium ions, chloride ions. And when that happens, there's some precipitation reactions going to occur. We're going to make silver chloride. So here's our reaction. Our silver ions and our chloride ions are going to combine to make solid silver chloride. This is a good choice of something to add to the mixture because we know copper chloride is soluble. So the copper will not precipitate out, whereas the silver will. So that'll make our data nice here. So we know the only solid we're going to collect is actually silver chloride. Okay, so first step, find the moles of silver chloride precipitate collected. So this is just a matter of looking at our data table. The precipitate plus the crucible weighs 29.2598, and the crucible alone weighs 28.7210. So the mass of the precipitate alone, if I'm looking at my calculator, would be 0.5388. That is the grams of my precipitate. And I'm trying to find moles, so I need to do a calculation here. So 0.5388. And by the way, this is definitely the type of problem where you could be graded for sig figs on because it's a data-based problem. And I want to convert grams silver chloride to moles silver chloride. And looking at the periodic table, I know that 1 mole of silver chloride is 143.35 grams. So that gives me 0.003759 moles of silver chloride. All right, so part A is done. Now we're going to think about part B. I want to find the mass percent of silver in the alloy of copper and silver. So remember, mass percent just means mass of the part over the mass of the whole. So I want mass of silver divided by the mass of the whole alloy. Okay. And remember, we do not know a chemical formula of the alloy. You cannot, I'm going to try to emphasize this, you cannot find this on the periodic table. This is an unknown. It is undefined. We don't know what this alloy is. We don't know what the ratio of silver to copper is. Because I've seen some people look at the periodic table and just add up the masses of silver and copper to find the mass of the alloy. That doesn't work. We don't know what ratios they exist. It could be 90% silver, 10% copper. There's no such thing as a molar mass of a mixture. So what we need to do is we need to look at experimental data. So what's the mass of our alloy? Well, we weighed it. It's 0.6489. That's the mass of my alloy. 0.6489 grams. That's my alloy. Again, it's a mixture. And then what's my mass of silver? Well, I don't know that right now, but I can find it because I know the mass of silver chloride. That's what that stoichiometry just did. So, or moles, I should say. I know moles silver chloride. So if I have 0.003759 moles silver chloride, I know based on my stoichiometry up above, my balanced chemical equation, every 1 silver chloride requires 1 mole of silver. They react in a 1-to-1 ratio. So every 1 silver chloride has 1 silver. And then I want to find grams of silver. So I'm going to do one more step and say every 1 mole of silver, I should be writing mole here, weighs, if I look up on the periodic table, 107.87 grams. So that means that I have 0.4054 grams of silver. So back up here, 0.4054 grams of silver divided by my grams of my alloy, multiply it by 100 to turn it into a percentage, I end up with 62.49% here. Okay, so that's number 5. Let's take a look at number 6. I think what threw people off on this one a lot is dealing with the hydrate. So it's been a little while since we've seen a hydrate, but the key thing is when you see a hydrate, that's where you have this little dot here. It's an ionic compound that actually includes water in the crystal lattice. When you're trying to find the molar mass of hydrate, you include the mass of the water. So what that means, when I'm trying to find the molar mass of the hydrate, I'm going to take the mass of beryllium plus the carbon plus the oxygen plus the 3 waters, add those all up together. When I do that, in this case, I find that this thing has a molar mass of 151. Okay, so let's think this through. So we've got 3.21 grams of reactant, and I'm trying to find grams of products. This is just a mass-to-mass stoichiometry problem. So 3.21 grams of my hydrate. I'm going to write this whole thing out just to make sure we know what we're talking about here. First step is always going to be convert grams to moles. So 1 mole of my hydrate, I'm just going to write hydrate because that's easier than writing out the whole formula. If I add up the beryllium, the carbon, the oxygen, the H's, and the O's, if I add those all up, I end up with 151.03 grams. Okay, and if I look at my mole ratio, it looks like 1 hydrate, because there's one of these, makes 1 product here. 1 BeC2O4. That's beryllium oxalate. And I'm trying to find grams of BeC2O4. So I'm going to look up on the periodic table and find the molar mass of this thing alone. That's 97.03. So that means I made 2.06 grams of my solid. So and this is just a gram-to-gram stoic problem. The tricky thing is just figuring out how to find the molar mass of a hydrate, remembering what the heck that symbol means. Okay, I want to calculate the volume of water released. There is several different ways of doing this, but you can treat it like a stoichiometry problem, and let's see, how am I going to do it? I'm going to think about it this way. I'm going to start the problem the same way as I did up here and say, okay, I've got 3.21 grams of my hydrate to begin with. I'm going to convert grams of hydrate to moles of hydrate. So molar mass 151.03. And then I'm going to use my mole ratio to convert moles of hydrate, which is my reactant, to moles of water, which is my product. So in this case, it's not a 1-to-1 ratio, it's a 1-to-3 ratio. So every 1 hydrate is going to make 3 moles of water. So if I stop and solve for moles of water, it's 0.0638 moles H2O. And notice how they're asking me for volume, and I have a pressure, and I have a temperature, so that means I must be using PV equals nRT. So I'm going to solve for V. It's going to be nRT over P, and make sure you are careful with the units. This is 0.0638 moles. The pressure we're given is 735 millimeters mercury, which is the same as a torr. So if you look on your equation sheet, you want to make sure you use the right R value. That's the one that's 62.36. And the units are liters, millimeters mercury, Kelvin, mole. So my pressure units are good. Looks like I got to make sure my temperature is in Kelvin. So 220 plus 273 is 493 Kelvin. So it looks like all my units are canceling out except for liters. So my answer is going to be in liters here when I solve, and that will give me 2.67 liters.